Hello, hello. I'm Paul Thomas, and I'm with the Wenatchee Valley Astronomy Club. Thanks for coming out tonight to our end of the week event for International Dark Sky Week, the Dark Sky Celebration event, where we had two guests. We had one guest speaker already. We're about to have another trivia night, and after this, we're also going to have some astronomy if those clouds can break. Yeah, we're a small organization. We've been here for about 2 years, and we are our mission here is to connect our members, the families of the members, and our communities to the dark sky heritage, the night sky heritage that we have, and of course astronomy through outreach and social connections. We do have a lot of different events throughout the year. Over here on our table, we have, of course, we have stickers, and we have our events posted here as well. So please make your way over there when you can. We also have a lot of different displays that you can check out different night sky things. That's it for me. Well, I'm gonna hand you off to Virginia with the WRI. Here you go.
Thanks very much. Thank you. And we're using the microphone right now because we are live streaming and recording this for later. And so if we don't have a microphone, they can't hear us. So that's why, because you could probably hear me otherwise. But my name is Virginia. I'm the Community Programs Educator here at Wenatchee River Institute. And let's see. Show of hands, is this anybody's very first time attending a WRI program? Woohoo! Welcome. And welcome back. So we are a small nonprofit that connects people, communities, and the natural world. Let's see, I'd like to start us off with our land acknowledgement tonight. So this land acknowledgement was created alongside the Shimpish-Gwashu people. We are spreading the message they wish to be spread to the public. The land Wenatchee River Institute sits on is the ancestral homelands of the Shimpish-Gwashu, or Piscosa, or Wenatchee people. The Shimpish-Gwashu, meaning people in between, had villages positioned alongside the Wenatchee River and surrounding areas. Their ancestral homeland extends from the Cascade Ridge throughout what is now known as the Wenatchee and Okanagan valleys. The culture and economy of the Shimpish-Gwashu people centers on taking care of the land. They fish, hunt, gather roots and berries, basket-making materials, and medicines. The Shimpish-Gwashu are named within the Yakima Treaty of 1855. Language to establish the Wenatchee Reservation was never followed through, even with the needed surveying completed. Many Shimpish-Gwashu now live on the Colville Reservation, 150 miles northeast of Leavenworth. They were forced off their land here, and the U.S. government moved them to this reservation. The Shimpish-Gwashu people are still alive today. They continue to practice their culture, harvest their traditional foods and medicines, and hold their ceremonies passed down from their ancestors. Most people won't see or notice them, but they continue to be on the land they are connected to. Their traditional language is in Hamchin, an interior Salish dialect, and we would like to welcome you all tonight by saying hello in their language, Tilhust. We offer this land acknowledgement as the first step to amplifying Indigenous voices and recognizing the harm done to them as a people. We stand as an ally to recognize their connection to the land and their rights to practice their culture on these sacred lands. We encourage all to learn about the Indigenous peoples of the place you now call home. The Wenatchee River Institute is committed to sharing this land acknowledgement and following up with other actions to educate and be respectful. One way we educate our community is through our youth programs. So our educators have been out and about in the valley this week, all the way down to Quincy and up to Orondo, and welcoming students here on our campus to field programs. And then we have community programs like this and our other Red Barn events where we welcome amazing speakers. We're lucky to have so many amazing partners like the Wenatchee Valley Astronomy Club to help us with all of this work as well. And so tonight, I would like to welcome Roger Tabor. He was a fish biologist with U.S. Fish and Wildlife Service for 35 years and just retired last year. His first 2 years were spent on the Columbia River studying predation on juvenile salmon. For the next 33 years, he worked in the Lacey, Washington office on various fish ecology projects. Most of his work focused on juvenile salmon habitat and predation issues. As part of his work, he worked on several artificial light at night projects. And I'm excited tonight to hear about those. So please welcome Roger. And you've got your own mic. Nope. And I guess one quick microphone announcement is when we get to questions and things, if you could make sure to get this microphone from Paul so that we can hear your questions on the recording. Okay, thank you.
I know nothing about astronomy, but like people like the astronomers are out at night. I've spent a lot of my career also working out at night. But instead of looking up, I look down, counting fish. So what I want to do is just kind of go over an overview of kind of the work that we've done over the past 20 plus years or so, trying to address some of the lighting issues up in the greater Seattle area. First of all, though, I want to acknowledge the Astronomy Club and the Visit Chelan County for hosting me and supporting me in this trip over here to the other side of the mountains. It's been actually kind of a great little vacation. But also, over the years, we collaborate with a lot of different partners: USGS, King County, Fisheries, University of Washington, DOT, and then the city of Seattle. But I really want to emphasize a lot of this work that I've shown was done in collaboration with Dr. Dave Beauchamp, professor at UW, and then finished his career at USGS, done a lot of work on light pollution. Also, what I wanted to mention here too, when I talk about artificial light at night, basically I'm talking about light pollution. But ALAN is kind of the term that's oftentimes used in a lot of the literature nowadays. Started over in Europe and now is kind of commonplace. So if I say ALAN, I mean light pollution, or if I say light pollution, I mean ALAN. So anyways, sometimes I get them messed up. So, okay. So what I want to talk about, this is just an outline. What I thought I would do is give a few examples of fish and how light and fish kind of interact in some around the world, different examples I think that are kind of fun and interesting. And then just a quick little talk about ALAN and how it plays out in the aquatic environment. And then some work that we did looking at how light changes the behavior of juvenile salmon and what some of the ramifications of that are. And then talk about how this changes in light can also change the feeding pattern of a lot of their predators, and go over a few different examples of those different types of predators. And then lastly, kind of what's going on in Seattle, the management of ALAN, and kind of where we're at the moment, sort of the good side, the bad side, and give you some examples of things that are currently going on, which I always find kind of fascinating. Okay. Oops, the wrong way. Sorry. Okay, so the first example, these first few examples are some examples from when I was in some of my travels. But the first one is Lake Tanganyika. It's one of the big giant rift lakes in Africa. And this has been going on for thousands of years, where the fishermen there figured out they use fire, and then they use some kerosene lamps, and now they probably use some LED fancy lights. But anyways, they have figured out from eons that you go out at night and you shine some light out, you get the zooplankton come up, and you get this fish that's shown there, and the top one, it's a little sardine-like fish, and they all come up to the surface. And when then they all come up to the surface to feed, then they can be grabbed by their nets, as shown there. But then also, if you, in the case may be, you might get one of these big giant predators. This is a relative of the Nile perch, which people may have familiar with from Lake Victoria. But anyways, they also come up at the same time to feed on those sardines. So you can get this whole food web going based on this lighting. And this has been going on for a long, long time. Okay, so another one that I find very, this is from when I was diving down a few times down in the Caribbean, down in Bonaire, which is close to Venezuela, which I find really fascinating. So this is what you might see during the day up in the upper left, coral reef fishes moving around, very active, foraging. And then at night, a lot of them, not all of them, but a lot of them, they need to hide, they need to do something different so they're not vulnerable to predators. So they might do something like this with these blue tangs. They've gone from that to that, hide it in the corner and changing color. But the one thing that's kind of interesting when we would dive, especially if we were the first divers in, we would get these big tarpon, which can be about 100, 200 pounds, very large fish. And you'd be diving and this tarpon would sit on the back of your shoulder and it's just waiting. You're shining your light where see where the fish are. Well, the tarpon's doing the exact same thing and it's waiting to see where you put the light. And if it sees something really nice and tasty, then it'll attack that fish and nail it. So anyways, but it just shows you how adaptable these fish are. You use a little bit of light out there and they figured out that that's an excellent way to hunt. So anyways, another just ways to show you how light and fish can interact. Now another one, oops, sorry, I keep going the wrong way. My bad. And this one people may be very familiar with, and this is in Hawaii and Kona, where we have the manta ray dives. It's very, very popular. A number of years ago, there was a hotel, at least the story that I've heard was a hotel. They noticed the manta rays were coming around some of the lights close to the hotel. And then, that sort of morphed over the years to this very large multi-million-dollar industry of taking divers and snorkelers out there with some lights. You put the lights on the bottom, and you get this whole ecosystem. You can see at the very top, you see some small fish, but these giant manta rays come swooping in and put on quite a show for you. And at the same time, oops, what did I do there? Sorry, I must have waved too much. Let's go back, sorry. But at the same time, as that happens, you might get a bunch of other types of fish. And when we were sitting on the bottom, this moray came in right next to us, basically crawling between our legs. And it's actually out there foraging at the same time. So we get all these predators looking for a variety of different prey, including a lot of small fish. So anyway, it just shows you kind of how the light you can use the light in a variety of different ways and how you can kind of create this kind of, this total complex food web. Okay, the next example, I took a couple examples off the internet, which I always found kind of fascinating too. So this is from the space station a number of years ago. One of the astronauts was cruising by, and now the white light, you can see how well that's lit up there. That's Bangkok in Thailand. And then he was puzzled by all these green lights. You can see it's very large from space. You can see this very large green blob out there. And that's from these, a lot of the Thai fishermen going out there with all these green lights, and then they're trying to attract these squid. Similar to what you might think of people even do here in Puget Sound, where they use lights to attract the squid, and then they have it. But anyways, and this is also done on, a lot of the Chinese do this on very large commercial boats as well, using lights to attract a squid as a big fishery. But anyway, this usually shows you how kind of the scale of this operation. A lot of big fishing fleet. One other example I wanted to go over is this one. And these are a couple advertisements I took off the internet, which I think are kind of cool. The English up there, I don't know where it's from, but anyway, you can read that, and basically you create this whole little ecosystem foraging, and you attract some little fish, some big fish, and voila, you got this group of fish under this light, and here you have it looks like a shark coming in to feed as well. And then in the upper right I took this off of Amazon, and this is called the green blob, which is basically a series of LEDs wrapped around a coil, this long coil. It's very, very bright, and you can use the green blob to go fishing. I don't know what the legalities are, but anyways, you can buy this on Amazon. I can't remember exactly the cost, but anyways, it gives you a picture of what you're trying to do there, attract some small fish, and at the same time, you're attracting some larger fish as well. So anyways, it's kind of an interesting little device. We bought one to do a little bit of testing, but haven't got very far with it. So anyway, it shows you how you can attract fish and how they can be sort of keyed into these different types of light. Okay, so just to wrap that up, I just wanted to point out that you can classify lots of different, there's, thousands and thousands of different types of species of fish, but they can be classified into kind of how they would respond to light. Some are going to be positive phototaxis, they're attracted to light, and you can see here in our example, very similar to our superhero in this old Fireside cartoon, where showing a very nice positive phototaxis response to the lighthouse. But also then there's fish that are going to be very negative. You put a light out and they're going to be running, and there might be some other ones that are very neutral, particularly these large predators who might have, sometimes they might use the light, sometimes they may not, but more kind of as they their learned behavior, but overall they're probably kind of more of a neutral phototaxis response. So anyways, so now I wanted to just talk a little quickly about the light that goes on, particularly in the Seattle. And this is old. This is an old map. It's probably a lot brighter in it, but this shows you the kind of irradiance, kind of basically where the lights are. And you can see Portland, Seattle, Vancouver, British Columbia. Those are kind of the hot spots here in the Northwest. Boise, Spokane also showing up there. But basically showing these are the places where you got a lot of artificial lighting. And this is the area that we've worked in Lake Washington and Seattle, greater Seattle area, very bright area. So what is the last thing I wanted I forgot to mention here too, is that in the Northwest, some things are going on too, where you have this increased population, more infrastructure, more people, and then also on top of that, you get all these energy efficient LED lighting sources. So basically, it's getting, in a lot of situations, it's getting worse and worse where you just have more and more light pollution. Okay, so, oops, sorry, wrong way again. I keep hitting the wrong button. This is some data, this is a little old, but this is kind of what we see out in near Lake Washington and the Cedar. So the Cedar River flows into Lake Washington. So basically we have three different types of light that that influence the aquatic environment. So we have moonlight, we have sky glow, and we have direct lighting. So we have all three of those to contend with. Of course, moonlight, because that's a whole different, it's nothing we can do there. But sky glow basically is, it's really prevalent in a reflection off the cloud. So if you have more cloud cover, you get more reflection, and it can actually be quite bright. So on the graph here, this is measured from the urbanized Renton area at the mouth of the Cedar River on Lake Washington. So it's very urbanized, Tukwila industrial area, and we go up to more rural. Although this is an old data, about 20 years old, when it says rural maple, that's probably more residential maple. And so this graph is probably really inaccurate now. But in those 20 years ago, you can see the green line where it says overcast skies. You can see that it's about 2.5, maybe more times brighter than full moon. So the full moon is about 0.1 lux, and that's pretty typical, about 0.11 or so lux. And then on the bottom is if we had no moon, clear skies, we get a little bit of sky glow, but not a lot, but nothing compared to what you get on overcast skies. And if we all know Seattle, they do tend to have a fair amount of overcast skies. I'm sure we can all agree on that. One other thing I wanted to mention too, and all of these measurements, a lot of measurements going forward, is light intensity. I've used lux, and that's a measurement that I've used kind of over the years, but it's basically the metric equivalent of a foot candle, if anybody's familiar with that. But anyways, so I use lux. There's other different measurements that are out there, but for kind of me as an old timer, I'm going to use lux. It's what I've kind of grown up with. But as some comparisons, here I show the sunlight. Usually it's 50,000 to 100,000 lux. My office, when I measure, was about 60. So right here, we're probably maybe 30 or so. 30 lux, I would guess. That's a wild guess. And then the other thing that we're interested in is the areas where we have direct lighting. So we have bridges, apartment buildings, et cetera, where we actually we're actually having water or light that's directly on the surface of the water. So when we think about the sky glow and the moon, we might think of these as a kind of a weak effect, but over a very broad area. Whereas the direct lighting might be a real strong effect, but it's very localized. So which is more important? That's really debatable. It's hard to say because we're talking about a large area versus a small area, but one's very strong versus very weak. But anyways, both, I would assume, very, very important. But I just wanted to emphasize here that we have this effect over there, particularly where you get this sky glow on these overcast nights. It can be really bright out in the Seattle area. Okay, one last thing I wanted to just quickly touch on, and that is how light penetrates the water. Here is the different types of wavelengths. They're kind of in reverse order. They go from our long wavelengths, the reds and infrared, to our short, our violets. But anyways, the point being that blues typically penetrate the deepest. And there you go down to 120 feet, just assuming that's clear water. We can go down fairly deep, and turbidity's low. We can go, and then the reds and the orange and the yellows, they progressively are going to be attenuated in shallower and shallower waters. And our ultraviolets and our infrareds, they're going to get attenuated very quickly. But you can see here, even our red, it goes down to 3 to 4, like 3 feet to 10 feet or so. So it can still get down, but nothing like the blues, which go down the deepest. Okay. So in Lake Washington, we are primarily interested in these 3 species. On the right side, I've shown our Chinook, coho, and sockeye. I'm going to primarily talk about sockeye and Chinook. I'll just briefly mention coho. It's still very important, but I'm going to focus on those other 2. That's more where we have our data. Chinook's primarily important because that's the listed. It's listed under the ESA as a threatened as part of the Puget Sound stock. And sockeye is a major player because that's the big player in Lake Washington. Lake Washington being one of its major nursery lakes. Over here on the left is just a map showing, people are probably very familiar with. But anyways, we have Lake Sammamish, Lake Washington, and the Ship Canal, where all the water flows out to Puget Sound. The Cedar River is the major spawning area of a lot of the Chinook, sockeye, coho, etc. Sammamish River kind of just connects the 2. It's a really low grade and not a lot of spawning goes on there. But anyway, so we're really focused on the Cedar River, Lake Washington, and a little bit of Lake Sammamish, and the Ship Canal. Just to orient, probably people here are probably pretty familiar with that setup. Okay, so the first thing I wanted to go over is sockeye. So sockeye, the main strategies for sockeye is, these are the fry. So that when they come out of the eggs, they want to get down to the lake as quick as possible. The lake is their nursery area, but their spawning area is in the Cedar River, shown here. So it's about 20 miles long or so. The idea is to get down to that lake as quick as possible to avoid, they're small, just a little over an inch long, and try to avoid the predators quickly. So how they do that because they migrate at night, and then they go quick. They migrate in the thowag being the part of the cross current of the river that has the most flow. So you want to get in the middle of the flow, where the flow is the strongest, and get down to the lake as quickly as possible. And they can usually do this 20-mile or so journey in 1 or 2 nights, depending on where they come from. Of course, if they're spawning down low, they have a short distance. Higher, they're going to have a longer distance. But they can do that in 1 or 2 nights. They can, depending on flow conditions, etc. But generally, they're moving down there quickly, and they move down there at night. So the key is no light. So this is what happens when you add light. So this is data that we collected, you see, a number of years ago. It's quite a while ago. But in the top graph we set up some lights. So the river is quite wide. It's a good sized river. It's probably similar to the Wenatchee, a little bit smaller, but similar. But anyway, so we set up some lights just on the shoreline. So, and then we knew there was a lot of sockeye moving downstream of that. We set up some lights, and we had there's a control group where we put some lights, and we had a moderate amount of light, and then some places so it was a little bit bright. And then you can see that as the time goes on, we had our lights on, and then on the y-axis, you'll notice there's fry abundance. It's on a log scale. So even though those lines are pretty close, there is quite a bit of difference. So you're going from a difference of, say, 100, 200, all the way up to 400 or 500. So in this little area where we set up some lights along the shore, we were able to coerce 500 or so little sockeye to come to the shoreline and hang out with us. So this shows you that if you were to take a bridge and you were to span it and you put it on here, there's like 10, I've heard of 3 lux will work pretty well. But you could span the entire river and you could basically stop the entire migration. So what would this might mean for predators or losing, how many you might lose. But anyways, we did, after this was over, then we went back and we shocked or electroshocked, sampled the fish that are in that particular area where we had our lights. And the control, of course, means that there was no lights there. But anyways, the control, we didn't see any predation whatsoever. We saw a moderate amount of predation in the stomachs. So the number of fry that were in the stomachs. And in the bright, we had a fair amount. So a fair amount of predation was occurring in this bright light. So these fish were zooming down the river, they eddy out, and then they're vulnerable to these type of predators. And this is a sculpin here. People are familiar with them, but they're basically real small little fish, little ambush predators that look like a rock, and something zooms by them, and they'll nab it. I just wanted to point out one thing that's kind of interesting. The interesting thing about sculpin is that when we took them to the lab, because we did a whole series of different experiments. We took the sculpin to the lab, and in the upper left, you can see here, when we put them in the lab, in a place where they have light or dark, and we did a bunch of light experiments in between this, but I took the extremes, 0, the control with no light, and 10 lux, fairly bright, which would be similar to this room, that the sculpin did much better preying on the fry under pure dark conditions than they did when there was a lot of light. So it's kind of the opposite of what we saw in the field. Now the reason for that is basically it's kind of an encounter rate in that if you go back to the graph I showed you where you had 500 fish versus 2, it's the encounter rate where a sculpin would encounter 500, but it has a low efficiency of preying on that, or you can encounter basically nothing, and then you would, even though you're more efficient preying on that, you wouldn't be able to get anything because you just wouldn't encounter them. But anyways, I wanted to show one of the reasons for that, and that is that the sculpin they have this sort of really complex lateral line system, a series of pores across their head. It's shown on this here in the lower left. You can see this is a cutout, and they really emphasize the pores. It's basically part of the lateral line system, but in sculpin it's very elaborate. Covers their whole head, and this enables them to detect things, fine movements in and around their head, and then they can strike at that much better than in most other fish. And in the picture here shows the sculpin, you can see the little dots across the head, and enables them to prey on these sockeye. So that's kind of interesting now that even though this fish is not very efficient at catching fry in lighted conditions, they do well because the light has changed the behavior of the fry to eddy out, to go to the sort of the edge of the water, or the edge of the water, the shoreline, and then they're more vulnerable to predation by this particular fish. Also want to mention that there has been some experiments with sculpins where they blinded them, and they do fine. They don't need, they don't really need, the eyes are there, they're important, but they're not essential. They do fine if they're blinded. So they're pretty adept at feeding in pure. And Lake Washington, it goes down about 200 feet. The sculpin are down there 200 feet doing fine, and there's no light down there whatsoever, and they're pretty happy. Okay, so that's kind of what I wanted to go over with sockeye. Sockeye migrating downstream, they hit with some lights, they eddy out and make them more vulnerable, particularly to sculpin and perhaps some other types of fish, which we'll go into in a bit. Okay, the next thing is, I want to talk about Chinook. So Chinook, can do whatever they want. But anyways, they can stay in the river, they can stay they can go down to the lake, they can do a lot of different, they go down the estuaries. Every population does a little bit different. But in Puget Sound, we primarily have what we call fall Chinook. A component will go to the estuary, a component will stay in the river and rear. But ours, they only like to be in the freshwater for a few months. They come out of the reds in, say, January, February, and they'll leave and go out in the ocean in June and July. So during that time period, that short as sub-yearlings, so they're not in the lake system that long. So this is when they get into Lake Washington, and this would also would apply to the Cedar River. It's going to be the same thing here, but they really like the shallow water. Whereas sockeye are adapted to being out in the middle of the lake, and they go out there fairly quickly, but Chinook like to stay close to the shore in really shallow water where they have a little bit more protection from their predators. So they like this, and this shows an example there from Lake Washington. Oh, sorry. Is that my waving my hand? Probably. No, it's the system. Sorry. Anyways, I'm going to talk in too long. So this is some pictures. This is what happens when there's no light. So if you go out there at night, this is what you should see. You should see Chinook just sitting on the bottom and chilling. It does nothing. It just sits there. You add light, and this is what happens. And this is a picture I took directly under this actual, there's a boardwalk at a park there in the south part of Lake Washington. This is what changes. They basically wake up and think it's daylight, and they're swimming around. They're active, they're schooling, they're eating, doing things that they should do during the day. They're not acting like this one, which is what it should do, which is basically just sit there, and then when the dawn comes up, then they would start foraging. But it shows you the huge difference in behavior of those two when you add some type of light, like shown in that one up there. Okay, so what we did, we wanted to test that and see what are the sort of the numbers show that if we added some lights. So we did the same sort of thing. We set up some lights. This is what we did in Lake Washington. We set up these lights and you can see where we kind of measured it out. And then after we let it run for a couple hours or so, then we'd come back in with a seine. This in this example is a red light, but I'll get to that later. But anyway, so basically then we seine them up, count them, and put them back in the water. So to see basically how many are being attracted to the lights. And try and get some information on if they are in fact very positive phototaxis. So this is the data from that. I only have just one data. I have a bunch of other ones, but I won't go into that. But anyways, this is kind of what it would look like in March. So we have March, April, and May where we did these certain trials. Each bar represents a different light. So it's a different light set along the shore. And then we did some bright ones and dim ones and some controls in March, and that stands for fork length. So in March, they're that's about 1.5 inches. April, they're a little over 2 inches, and then in May, they're a little over 3 inches or so in length. So they're getting bigger, and as Chinook get bigger, they move into sort of deeper and deeper water. When they're real small, they're in very shallow water at less than a meter, and as they grow, they get a little bit more sort of rambunctious and can move offshore. But what I think is important here is that in the upper far left, you can see in this bright light, in that little seine net, we were able to attract upwards of 400 Chinook, which is a pretty, it would look something like this, where you get all these little Chinook that are clumped around that little light. And then on top of that, there was some sockeye in the group as well. And one year we had a bunch of sockeye. Sometimes we might have 700 little fish that we had actually attracted to this light in this one little spot. And then we repeated this in Lake Sammamish, and we saw the same thing with coho. And that's pretty much all I want to say with coho. But anyways, the same sort of effect. The Chinook, sockeye, and coho all showed the same sort of effect where they're attracting to the lights. Oops, and then I did it again. Okay, so now those are more or less fry when they're real small. So now what happens when they get larger and they want to head out to the ocean? And so then we did some, it's hard to deal with putting lights up and catching because they're just big and fast and harder to deal with. So then we did a lot of, and this was for a whole set of other work that we did, but this was, we did some ultrasonic tagging. So we have a fish here as a Chinook, and we put in these, implanting a sonic tag, and then this is one of the locations where we set this array up. So the red line is the outline of where we had coverage from our listening devices. And we had a number of listening devices, and then we can get a signal from each fish, and then we can triangulate and get a position. This gives you a resolution about less than a meter. So it's pretty darn accurate, and this shows you where these fish are migrating. So what we were interested in is how they're moving along the shore and what kind of habitats they're using. This was some work we did. This is the Seattle Tennis Club. You can notice the size of the tennis courts there, and their big building. There's a swimming pool. But they were gracious enough to basically let us have their shoreline to do some of these experiments. And then we used their power from their facility. So it worked out great. But anyways, this photo, this one, and so in this analysis here is sort of a heat map where the brighter the colors, as you go from blue to red, you're getting more and more usage. So wherever there's a red, and you can see around the docks there, the fish are moving. This is movement during the day. So I just wanted to show this as kind of the kind of information that we are collecting. So these fish are moving along the shore. This is Lake Washington, and they're very tight to the shore. So when they're out migrating, these are smolts. They're heading out to the ocean, and they're very comfortable just swimming along the shoreline. So the next one is sort of the key graph, and this is from the 520 bridge. This is the old 520 bridge. It's long gone now, been replaced. But the key thing here is that we were real puzzled when we first saw this sort of pattern, but then we overlay it with the light. So the yellow dots are the overhead lights that are spilling onto the light. And you can see all of the fish are really strongly attracted to those particular lights. And then you can even see there's two sets of like parallel lines. So that would be the shadow line from the one. So there's a spill from the first line, or the light that's closest to the water, and then there's a spill from the opposite side too, and that shadow line. So the fish are keying into that shadow line as well. So this is all done at night. And then also we have down here is an apartment building, which adds this other set of lights. They also like those lights there down at that apartment building, and they're hanging out there. So just to orient you too on this bridge, so if you go up north and hung a left, then you're in the Ship Canal and you're heading out to the ocean. And you'd be not far from the University of Washington. So then this is another, just saying the same sort of thing, but just shown in a little bit different way. And these are sort of individual tracks. So each fish is a different color line. That's the I-5 bridge. People have probably been over that many times. It's that, then it has the shadow lines, so it has the overhead lights. And so you have the bridge. You see the purple dots are the lights. And then directly under the bridge is the cross lines, and then the diagonal lines are the shadow lines. And you can see very clearly how the fish are oriented at night along those shadow lines and moving back and forth. And then an interesting thing here, at this particular site, we also have a lot of bass, and we lost a lot of our fish at that spot. And it could have been related to this lighting effect, but we're not sure. But anyways, and then the 520 bridge shows the same sort of thing. You can see that double line where we have the shadow lines, the old 520 bridge, and these fish are moving back and forth across the shadows. Basically showing how these fish really orient strongly to these lights and how they use them. So then the last thing I wanted to talk about affecting fish behavior is some work we did a number of years ago to look at kind of what we might do to, and we talked about earlier this afternoon about looking at the spectral composition. So we tested these four lights. I'm only going to show the data from the second year. We added a couple other lights the first year, but I'm not going to go into that. But anyway, so basically we have these four LED lights. We have our 5,000K, 2,000K, and a yellow filter and a red filter. And the idea was to test these to see kind of what the attraction. There's been some research with a lot of juvenile salmon. So they're real sensitive to the blue light. So then the idea is to get rid of that blue light. So we want to get rid of the blue light as much as possible, and that's why we test. And then we were working with these light engineers. And what they were really particularly interested in was the yellow filter light. So they thought that if that would be commercially viable, it would be a really positive thing in the direction of helping salmon. Anyways, so this is the same sort of experiment setup. But we have that's a yellow, red, and there's a control in between those, and then that's the 5,000K. In this setup, we didn't use the 2,000K just because we try to keep it as simple. And we also recognize when we push the red, we realize that's not very practical. People would not ever really want to use it, but we wanted to use this more for experimental purpose to see what would happen. So we really expected that they would avoid those. They would select the yellow, select the red, and they would avoid those other two. But that is exactly what did not happen. So it was all the best. We had light engineers, and they had this great idea. We're going to test these, and then we'll go forward, and we'll have these beautiful yellow filter lights everywhere. But anyway, so this is just 1 year. This is results of 1 year. Here's our control, no lights, our LED red, LED yellow, and then our 5,000K. We did not see any difference across, and we did this for 2 years. There was no difference between any of the lights. The fish were attracted to every light, whether it was a red, yellow. The only thing, of course, if there was no light, they weren't there. There was no attraction. But it was exactly what we did not expect. But anyway, so it's very informative, though. And I'll get down to kind of the ramifications of that anyways. But this is shallow water along the edges of Lake Washington where you might have a lot of homes, a lot of docks. So data like this can still be very, very important, very informative. So that's kind of what I want to talk about as far as the effect of how lights might affect the behavior of the juvenile salmon. But now I wanted to switch to talk about how the lights are going to affect some of their predators. And so we talked about sculpin. This is the Lake Washington food web. But you can imagine a food web, something similar, a little different, of course, in one of the rivers. Simplified but different. But we have these very complex. And here's a quote from this book, which is now probably quite a bit outdated. But it's a really nice book, a good review, all the different factors affecting light pollution. And that is that basically they're saying that you add some light and you increase the predation efficiency of a lot of predators. So basically, adding light it can be very detrimental. And the idea here is that basically, and so each one of these arrows is showing the strength of that linkage. And then if you add the light, those can change those linkages, and so the whole food web could change drastically. So anyway, just showing the food web is complex. You add light, and a lot of these predators can take advantage. We talked about sculpin, where the light doesn't seem to really matter. But these other fish are more visual predators, and that can be really important. So here's an example of some work that was done with lake char and rainbow trout, basically showing that as you add light, as soon as you add some light, so we go from dark, and then we had some, we're going up to 1 to 2 lux, but you get a quick jump. As you add more light, these fish are more predacious. Their foraging rate goes right. Now, sculpin would be probably somewhat the opposite of that. But in these two examples, and we can think of a lot of the other examples, a lot of the other fish, that they're very visual oriented and they can be very effective with a little bit of more light. Now, the one reason we use sculpin in a lot of our, because they're small, they're easy to work with, and they're very plentiful. Dealing with these guys is very tricky. It's very hard. They're large, mobile fish, and a lot of this work is done in the lab. But applying that to the real world can be a little bit tricky at times. So we kind of have to infer certain things or do some other types of analysis. So once again. This is some work that I wanted to point out from work that Dave Beauchamp up at UW was working on. And basically, he was showing that a cutthroat trout moving through the water is kind of like a cylinder. And as during the day, you saw in the day, and then at different depths, at dusk, different depths, night at different depths. So the small fish that cutthroat are after are schooling, and you may never encounter them. As you can see, he never encounters them, and then you go down deep, he gets smaller and smaller. Basically, as you go down, the amount of area, his encounter rate gets smaller and smaller. And then at dusk, the schools, a lot of these smaller prey fish, they break up, and that's where they have the advantage. Even though you can see their circle rate, the area that they can encounter fish is smaller, but because the behavior of the prey fish has changed, they will have a higher encounter rate. So basically, dawn and dusk are typical of these large predators, that there is their sort of peak feeding area when they have the advantage and they can prey on a lot of these smaller fish, which would include a lot of our juvenile salmon. And I also wanted to point out that this is kind of a general scope of what it looks like in the lake, but if we add turbidity, this whole thing would change, it's going to get much reduced. Turbidity is also a really big factor in how a lot of these prey fish are perceived. Okay, so Dave, when he was doing some of his analysis, he did some work back in the 80s, and now and then he tried to compare it to work that he did in more recent, what is he doing here? 85 versus 2005. So, and over that period, there has been a large increase in ALAN, or light pollution. And so what he did, some of his calculation, he thinks that you've gone from on the far right here at night, you don't see very much predation. Basically, the predators don't have a lot in their gut, to basically they're able to feed now all night. We had all this extra sky glow, all this extra artificial lighting, and the peak feeding can change and he estimated from approximately 3 hours a day to 8 to 15 hours a day now. So things have changed a lot, where the whole lake is just getting closer to a dawn-dusk period, and enables these predators to prey on a lot of our either juvenile salmon or in this case also smelt that occurs in Lake Washington. Okay, so the last thing I wanted to go through was, as far as predators and salmon, was some stuff that we've been working on just recently at our office. I'm just helping out a little bit. But anyways, there's some work that's been done down on the Sacramento River in central California. It's been very successful, showing how you add some light and you can increase the predation risk. And what they're doing basically is they're using these tethered devices. Basically, it's basically a fishing pole. You add a fish to it, and then you kind of time when that fish is lost. Has a magnet on it. So you can either do it, these ones here just kind of float down the river, the one on the upper right or the one on the lower right, and this is like a fishing pole. So as a magnet, you have a tethered fish that's hooked, and then basically you add it to when you might have some light or some non-light, and then you can estimate survival times based on that. We use hatchery coho, but we're trying to do this in Lake Washington as well, to see kind of how much change there is if we in an area that's lit versus area that's not lit on the survival of these tethered fish. So basically, it's kind of an indirect measure of predation risk. It's because basically you're looking for the change in the behavior of the predator, nothing to do with the predation of the prey, because the prey is stuck on that line shown here. And we used a bunch of hatchery coho for these experiments. So I just wanted to show, this is, once again. These are some survival rates that when we did from last year's work. And basically shown here that predation risk was about 8.5 times greater in the lighted area than the non-lighted. So basically showing that, yes, you add light out there, fish are going to get eaten, and they're more vulnerable to these particular types of predators. And this shows the survival over time. So you can see how your probability of survival in the dark versus light, the light being on the bottom, that you're going to get eaten pretty quick. And on the top, you're no light, you're dark, you're doing pretty well. So anyways, there's quite a bit of difference between that. So that was some work that we started last year. And then this is just some observations from that. And so what we didn't do a really good job because we have dark and we have light, so it's hard to tell what predators. But what we did observe, on a couple of cases, we did catch the fish that were eating. And up here is a sculpin, a prickly sculpin, and then a rock bass. I point out, and these were caught that were eating on our tethered fish. And then these are other ones that we observed feeding. That was yellow perch and cutthroat trout. Of those 4 predators that we just mentioned, rock bass and sculpin can both prey pretty well at night or in low light conditions. So that's kind of what you'd expect. But the other 2 are kind of interesting, and yellow perch and cutthroat trout primarily is a dawn dusk feeder, whereas perch is more of a day feeder. So it was kind of surprising to see all these perch up foraging around in the middle of the night that usually you don't see. So it basically shows where we add light, you have these perch, which are very numerous in Lake Washington, can start feeding. And then this graph here just goes, the solid dark line is the dark, and the yellow is the light. And basically, you can see the difference as they go. But the difference is here in this one here, May 19th, the temperature dropped unexpectedly. We had a cold snap, and basically everything shut down. There was no feeding. So basically, they ended up being about the same. But it just shows you the importance of the effect of temperature on this. But the other thing I wanted to point out too is rock bass is a newcomer to Lake Washington. It's only been there for the past 20 years or so. We never used to see it, and now it's becoming very, very common and more common than smallmouth, largemouth bass. And the scary thing is they feed at night, and they feed heavily on sockeye fry, so they have been kind of a very worrisome new predator so you can see sort of all these other factors. We add in the factors of lighting, but also we add these new predators on top of it, and you can see where some of these young salmon may have trouble. Anyway, so that's what I was going to go over with fish predation. Now I wanted to talk about some of the other predators. And this is the main predator where we see on our shoreline of Lake Washington, and that are great blue herons. So when we did our experiment here, this is similar to when we did our beach staining in Lake Sammamish. Of course, we had a heron come right in. So these are temporary lights. We put out the lights, and sure enough, the heron comes right into our little square and starts feeding. It shows you how adaptable and quick learners they are. But we do, in a lot of cases, in and around Lake Washington, Lake Sammamish, we do see herons feed under strong light, where there's a light, and then oftentimes under those light, we know there's a lot of Chinook there, and we see herons that will feed there. So they seem to be one of the primary type predators that really of concern for where we have lights, we have herons, and they are a very highly energetic, very adaptable predator, very smart predator. We've also seen grebes, but we haven't seen many grebes around lately. But this is probably the main one where we really see really effective with great blue herons. And lastly, I was going to talk about the last thing is harbor seals. We don't really have any data on harbor seals, but we do have a large number of them that are at the mouth of the river. But at the end of the ship canal, I should say. And there has been some research done up in Canada, BC, this one particular spot, Puntledge River in the Vancouver Island, where they have a couple of bridges real close to the mouth of the river. And this community, I think it's called Courtney or something like that. Anyways, they use those bridges, those shadow lines, and then when the Chinook smolts come by, they prey on them. And they've been trying different methods to try and kind of reduce that predation, but using city lights to help them prey on smolts. Now, as far as predation on adults, I'm not really aware of anything, but I wouldn't be surprised that there might be something out there where sea lions, harbor seal, whatever, could be using lights as well to help them prey on some of these salmonids. So I'm running a little bit late. I'll go quick. So in summary, I talked about how these 3 different species are attracted to the lights, and because they're attracted to these lights, they're more dense, it makes them more vulnerable, and also the efficiency of a lot of these predators can greatly increase with the lights. And here's a picture from where this is what we want, no just fish hanging out in the middle of the night, and this is a photo with where they're under some lights and they're active up in a school around foraging. These are some Chinook. Okay, so the last thing I want to talk about is sort of management of what's going on. We've documented it's an issue. Back in the 90s, we didn't get there wasn't not much done. We get a little bit, but not much. But here lately, we've been getting a lot of traction. There's been a lot of activity going forward, looking at and trying to address this issue. But a number of years ago, we did see stuff like this, where we talked about how we could do 22 lux and it's not really a problem. Or here's this other federal agency saying that they've seen studies where that increasing light favors this juvenile salmon over the predator, so it's not a real big deal. But anyway, so these things are really, they're out there and they're very wrong. So this is kind of the things that we're trying to change. But here lately, I think things have been changing quite a bit, and we've been getting a lot of good feedback. And this is from the King Conservation, and they've been trying to work with a bunch of municipalities around the Lake Washington area, Lake Sammamish area. And then you can see here at the top, they have a couple key takeaways, and they're trying to do education and reach out to these municipalities and trying to address artificial lighting. So the number one thing is they're basically saying, yes, Alan, it's important. We need to address that. And the number two, they're talking about considering light levels that are around the same output as the moon, which, as you remember, was about 0.1 lux or so, approximately. And that seems like a reasonable approach. If we can, that seems like a really good threshold. If we can do something similar to what the moon is showing us, I think that would be definitely a step in the right direction. And here's some of their other recommendations. The one developing some guidelines, and then the 2011 model. This is from the Dark Skies Initiative. And then zoning and planning processes, which I really don't know much about, but anyways, definitely a step in the right direction. And then lastly, community outreach and education. And I wanted to focus on that a little bit real quick. And this is a pamphlet for Lake Sammamish. They developed a really nice pamphlet to show the people, and this was distributed all around the different landowners or the people that live on the water, what the things that you could do. But really nice graphic about artificial light pollution impacts, sky, et cetera, et cetera. You can read. But anyways, the thing is you have the top five actions I thought I want to go through here real quick. Number one, remove unnecessary lights and never aim lights directly on the water. Exactly what you'd want. Use the light shielding. Shield the lights would be very nice. Timers, Jim White earlier, the first talk, he did a really nice job going through this. Energy efficient bulbs that reduce the brightness, all very good. And then the last one is use our warmer color temperature bulbs or their filtered LEDs, 3,000 or less, to minimize detrimental blue light, penetrate deeper into the. So that's one where, I have a little, I tried to get that removed, but I didn't get anywhere. They wanted that in there. But for me, this makes a lot of sense, but the danger is, I've seen people go, oh, another salmon-friendly bulbs. Well, let's just get a whole bunch of those and we'll run out to our house and put lights all around the house because we got salmon-friendly lights. So that's the danger. There's a good side and a bad side to that. And I'm not sure where I stand, but I'm not a huge fan of that part. But anyways, I was outvoted on that one. That one is in there. So it's good for out in the middle of the lake. It's a good idea. But along the shoreline, adding a lot of these bulbs is not going to do anything. And there is, I think, some people sell salmon-friendly bulbs, but I don't think there's really such a thing. It's really just less friendly or more friendly, but it's not a friendly bulb. Okay, the next thing I think I want to show was this is from the Seattle Shoreline Master Plan. And right off the bat, lighting should be first avoided, and then it goes through what, if you have to, you shield, blah, 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 do some other stuff. So this was really nice, and it sounds nice. And then one day this appeared, which we were really surprised. This is the Fremont Bridge, which is in the ship canal, and this is where all the fish must go through this to get to the ocean. And then also one day we saw this, like, wait a second, where'd this come from? You can't do that. Anyway, so this ended up being a Seattle Art Department project, which we were not aware of, and I don't think a lot of people in the Seattle did not know about it. But they thought, oh, that's pretty cool, let's just do that. A number of years ago, the mayor of Seattle had gone over to Europe and seen some really nice bridges over there, and he wanted them. But we were able to squish that idea, but then all of a sudden, boom, a few years ago, this appeared. And then they were planned this also for the Ballard University, a couple other bridges as well. Like, oh man, that's just ridiculously bad. Anyway, so last I heard, and I'm not sure, I don't know if I trust them, but they were gonna turn this off or greatly reduce it during the smolt out migration period, which would be basically April to July or so. During that window of out migration, you would turn the lights off. At least that's how, I don't know if I trust them. But anyways, that's where we left it. We weren't really too thrilled with it. But that shows you how, you kind of have, 2 steps forward, 1 backwards. But it's over and over again. Okay, a couple other examples. And we'll quit. But this is 520. So remember I talked about the 520 where the fish were lining up along the bridge. So this is the old bridge. And then this was replaced a few years ago with the new bridge. Greatly better than it was. It used to have all overhead light, and now it has a lot of deck lighting. They changed it, and a lot of that was because we were working with DOT and told them that we really need to change that. So, and you can see a lot of the little small. There's a little bit of overhead lighting, but not a lot. They did add some for some bike lanes, but I don't know how bad it is. But anyways, it's a lot better, not perfect, but it definitely shows you a step in the right direction from the old bridge to the new bridge that goes over Lake Washington. A lot of people probably have gone through that. Okay, the next example is also kind of an interesting example. And this is the Boeing facility at the end of the South Lake Washington. And this is what it appeared in 2017. It was really bright. And then there was some discussion, and then they shielded the light. So that's where the real bright lights are. That's where they bring the airplanes out of the hangar and then they move them over to the runways or whatever they do. But anyways, very bright. They added, I think there were some big LED lights they added, which is kind of ironic because we had worked with Boeing years ago about lighting on the Seattle River. But then again, these things happen over years, they just forget about it. They decided, we want lots of light. But then there was a lot of blowback, and then they shielded them, and now it's quite a better. Not great, but not bad. Anyway, so this picture here is taken directly from that light. You can see the arrow? That exactly where that light, it showed there's a bunch of Chinook that hang out under one of those lights. So it was greatly improved. Now, the interesting thing is, from the story that I heard, I don't know how true it is, but this had nothing to do with salmon. The reason it was shielded is because the people on Mercer Island was a very wealthy community. They were not too happy with these lights shining into their houses. And so then they shielded them to make it, so they got a lot of water out, but it had nothing to do with salmon. At least that's, I'm hoping that maybe it had something to do with salmon, but I'm not really optimistic about it. Anyway, so that's the Boeing facility. But also I will point out too, here on the left, on both of those pictures, you can see there's some cranes there. That's there's a new convention center, hotel, et cetera, there being built. And last I remember when I was there, they seemed like they did a really nice job. They didn't really have a real light imprint on the water. They had enough of light for what they needed for the hotel and the convention, but they didn't have much spillover. So they seemed to had probably worked with the city of Renton and did a real nice job of trying to reduce the light on the water. Okay, so the last thing I want to mention, this is something that's ongoing now, and that is USGS has been doing a real big project, sort of a baseline inventory, and looking for areas of high elevated Allen, and that is going around the Lake Washington, Lake Sammamish, and collecting a lot of really nice data on what is actually out there as far as light, and then that can be used in a whole variety of different ways moving forward. So there's a lot of things that are going on. So like I said, there's a lot of good things, and sometimes it doesn't work out as well as we hope, but it's moving forward. And the last thing I wanted to point out, this is something totally different, but this is a bridge down in California. It goes over the Sacramento Bridge. Sacramento Bridge, this is the Sundial Bridge, really fancy bridge. If you're ever down there, it's right off the I-5, you can stop in and see it. But when they built this, the idea was that we're going to light up that river if we can. And so when they built this, they had lights going all the way across the river, the entire width, very fancy. But then they started noticing that they had these big, huge rainbows that were all sitting underneath the bridge, foraging like crazy. And so then there was a lot of concern because we have endangered Chinook. What about the Chinook that have to go through this? And you just lit up this bridge. It's a walking bridge, a pedestrian bridge, but it's very, very, very fancy and sort of state of the art. But anyway, so what they did is they turned it off when they have a hatch release, or they think there's a lot of Chinook going by. They'll turn the lights off at night, and then they'll use it different other times. They have the control where they can use different light levels and different types of light. But anyway, so there's a lot of things going on in this spot as well. But it's a kind of an interesting location where they built it with no concern whatsoever for artificial lighting, and really just lit up the river. So it shows you what you can do, but then it also shows you how you can kind of remedy the situation to at least some extent. And so that is it for me. And then lastly, this is another picture I took under the light. There's the light, another cartoon light. But anyways, this just shows you a good example of what you don't want to see. Our fish are running around acting like it's daytime. So we try to avoid this as much as possible. So anyways, thanks for having me. Hope that was somewhat illuminating for a non-illumination talk. Thank you. Oh, anyways, and this is my email now. If anybody has any questions or would like further information on some references or something, just shoot me a line. Okay.
Any questions? Yeah. All right, I've got a question. Way back with the manta rays early on, do you have any evidence of that being bad for the manta rays?
I have no. Yeah, that's a good question. I have no idea. But it's a real big business, and there's a lot of food for them to feed on. And, I don't know. I couldn't answer that question, but that's an awesome question. I have no idea, but it's truly spectacular. Even though for me, I don't like lights, but it's still I really enjoy going and seeing that. It's fascinating as can be to see giant animals that run around under the lights. But I'd have to look that up. That's a good question, though.
Okay, I got one second one, and then I'll pass it off. I promise. Why green lights? With all of these fishing things, it seems like blue.
You got some good questions.
But they're green.
I don't know. When I've looked at it online, most of the, I don't know where that came from, but our green blob is bright green, and I don't know. Most of this stuff I think comes from more Southeast Asia area, and why they're using green, I don't know. But that seems to be pretty common. A lot of those countries use that bright green. Yeah, They started that way, and they're still at it. The Chinese ones I've seen, they seem to be more of a full spectrum. They seem to be more of a bright, you see the big squid Chinese fleet. They use some real bright white light. Theirs is not green. But most of the green stuff I've seen seems to originate from more Southeast Asia area. But I don't, that's a guess. But it's a good question.
So you were talking about the Boeing building, and that reminds me of a lot of local issues around here, like around the fruit packing buildings, where they have large buildings and really bright lights that illuminate the surrounding area for forklift operations, I'm assuming. Who approached Boeing? And
they're a giant corporation, and we've worked with them and we've gone on their property, but dealing with them it's just a giant bureaucracy. It's like dealing, excuse me, it's like dealing with the military. I mean, you have to get a badge, you have to go through this process, and we have our contacts with them, but I couldn't answer that.
You said they changed because of homeowners primarily.
That's what I heard. That's what I heard.
Not for the salmon.
That's what I heard. That's what I heard. Now, I don't know how accurate that is. Like I said, it's a giant corporation. I get tidbits of information, so I could be way off on that, but we did work with, we got funded indirectly from Boeing. Originally, when we did our original Cedar River work, was from Boeing, and we told them, keep those lights down, and I think they followed that. But as a lot of cases, it was 20 years ago. So a lot of those people that were there, and they were, the biologists or whatever that were involved in that, they retired, and then the new person shows up, and they're like, oh, whatever, they do something different. I don't know. But, 20 years ago, things change, and people have different perceptions. And then they're like, wait a second, let's put some lights out there.
Option that feels like a game of whack-a-mole.
Yeah, exactly. That's a good. Yes, it's very true.
Not sure how to approach.
Yeah, it's not an easy. Yeah, it's a very difficult. The thing that's interesting about that, the lights is a nice, easy thing to fix. But the problem is, it's also a nice, easy thing to alter. Whereas if we know, like for example, bulkheads, armoring, it might be bad for a lot of the Chinook along Lake Washington. But changing that, extremely difficult. But nobody's going to be adding it either because it's extremely difficult to add it. But lights, on the other hand, is the total opposite of that. In that you might be able to fix it really, but it's also very easy to change it, to add a bunch of lights. So it just takes one person. Oh, I'm putting a whole bunch of lights out there. It can be done. And you can start with that art project. That's right downtown Seattle on Fremont. And all the salmon got to go through that one spot at the choke point, and you put up a whole pile of lights under there.
To answer your question, for green lights, why fishing boats use green lights, it says fishing boats use underwater green lights primarily to attract fish and marine life at night. Green light, negative 520, negative 570 nm, penetrates water better than other colors.
Okay.
So that's why they're using it. And it draws the plankton, which brings in the bait fish, which attracts the larger predators, so on and so on.
Okay.
Yeah, the question is why don't they use blue light? Which would you think would penetrate even better, but maybe that's more expensive or something I don't know. I've never seen that. Maybe there's something tricky there.
I just have one more question.
Sure.
What can we look? Two-part question. Is your team still continuing the work that you've done? And then what kind of work can we look
So the only thing they're doing right now, there's a lot of other. There's a lot of in Seattle. There's a lot of different agencies doing a lot of different things. So there's a lot going on at USGS. University of Washington is involved in some projects. Our office is involved in some projects. So there is a lot of right now. There is a big impetus to do research on artificial lighting at night issues. So it's a big issue at the moment. So you should be seeing a lot more coming out, publications and a lot of different things, and hopefully, and there's a lot of the public outreach stuff that one example I showed. You'll probably see a lot more of that kind of stuff coming out as well. So I think it's overall, there's a step backwards, but I think the overall progress is forward. It's getting better. But then on the other hand, there's more and more people moving there, and there's more and more LEDs, and so yeah, you could argue it either way. But overall, I think it's a good trend.
Are there any more questions?
Okay, so I don't know how you would do a test for this. So if you don't have info on it, that's fine.
Sorry, say it again.
I don't know how you would test for what I'm about to ask for.
Oh, okay.
So no worries if there's not info on this. But do you know of any research about that sort of indirect full moon level general light pollution versus like a control area that didn't have that sort of light pollution? Like what effect is that like full moon illumination in an overcast downtown Seattle day having versus like less light pollution, like maybe an overcast day versus not an overcast day, or? Well,
the only thing I can say when we did our stuff in the, we did some, and I didn't go into this at all. We did experimental light levels in artificial stream channels. And then we used different levels. And that's where we came up. It looked like that 0.1 lux would be about the right level before we would see a change. And then you would infer that to the real world. But in the real world, and then we also did some other testing in the real world, which was all say about the same thing. That 0.1 lux was a reasonable level where you would start seeing a pretty good change above that once you got over that sort of that threshold. So there is it's not perfect, but there is a little bit of evidence of that sort of thing.
Cool. Because I just see it's hard.
There is also some work that was done in, I think, someplace where they call it the moon trap, and that is where the moon pops up, and then all of a sudden the zooplankton come up, and then they orient to the zooplankton, the little small fish, and then as the moon's up, then all of a sudden then they're vulnerable to the other, these big predator type fish. Also, there's a thing called the moon trap hypothesis about how the moon can come up over a mountain range and really change the whole food web very quickly. So there is some work, a little bit of work related to the sort of the effect of the moon.
Well, thank you, Roger.
Well, thank you.
And giving us your time. I know you traveled over the mountains and through the rivers to get to us. So it is a vacation, yeah. To stay into Leavenworth is never a bad time.